We are live. Back at it. Another day, another week, more awesomeness. Hopefully you're having a great holiday season. I hope it's been really enjoyable, peaceful, and you've really got to spend time with those you care about the most. Um, yeah, we've had a pretty good time. Thanksgiving was nice and smooth, quiet. We do Hanukkah, and it was a great week. Really enjoyed it. So Hanukkah, if you don't know, is an 8-day celebration. It's a little different than Christmas. I say a little, it's a lot different, but ultimately, really enjoyed ourselves. We got the New Year coming up in what, 3 days? So yeah, they still continue. By the way, so reviewing the last stream here at the desk, I'd mentioned that I got a new laptop. And when I went back and was reviewing some of the footage, I realized just how kind of choppy it was. It was more than just internet, so I needed to adjust some settings. So just feel free if it does end up being like super choppy constantly, not just little moments here and there, but like throughout the entire um, stream today. If the video feed specifically gets choppy, feel free to mention it to me. I am still trying to tune in this particular computer to get it working the way I need it to. If it doesn't work out, I'll end up just having to switch back to what I was using originally, which so be it, right? Um, anyway, that being said, I do apologize for last week. It I tried to do like a mobile stream. It ended up just getting all kinds of screwed up, so I just ended up deleting it, acting like it never happened, and here we are today. So, let's roll into it. Feel free to start getting your questions in. And if you haven't already engaged in chilleracademy.com, I'd highly recommend you at least go look at it, see if anything over there interests you. I do have a questions portal for this series, the Chiller Questions Answered series, where you can jump in there and be able to get prioritization, get your questions answered, and then I do take these streams and upload them into there to where you can review them within the portal there directly instead of having to always go through YouTube or something like that. That being said, I've also started something else kind of fun, and this led to today's fun fact. So I was recently reading, let's see, I was reading up on the CGAM manual, and it mentioned and this is today's fun fact, by the way, it mentioned the evaporator or having a refrigerant migration freeze in the evaporator, which I thought was super interesting, and I hadn't noticed that. And I did end up finding out, uh, well, I did some research on it, so I'm going to explain what this is today. And I'm surprised. It's actually, I've been around it more than I realized. It's one of those things where if just nobody really ever explained it, not necessarily all that obvious. I'd also know that part of why it's not something I've had to deal with a whole lot is because of my climate. So I'm here in Texas. We have super mild winters. And so I'll get into why that makes a difference here in a minute. But it's a fascinating concept. So why don't we go ahead? Let's dive into this fun fact for today. And this is something that I ended up seeing in the CGAM manual that later then translated into the RTAC manual or one of them that I was reading at least, had a really good explanation as to what this is and why the machine wanted to have full control of the pumps on that particular chiller. And then we're going to look at a YVAA example as to why they have a suction cutoff valve in the suction line, which, or one of the reasons why. I'll say it that way. One reason why they have that valve there now. So let's get into this. Evaporator refrigerant migration freeze. This is when we're in a low ambient state and we have a flooded evaporator or a falling film, but specifically flooded. Okay, so with a flooded, we have tubes that are fully submerged. These are the most at risk for this to happen, but this can still happen on falling film evaporators because there is still some volume of liquid getting held in the evaporator. We will come over here and we're going to look at some of these examples here in just a minute. So with that falling film, or with those types of evaporators, what can happen is in liquid refrigerant is naturally attracted to the coldest point in the system. So when the circuit shuts down and our condenser coils cool rapidly due to really cold ambience, once they start to tip down and they get colder than the evaporator is, like standing, what can happen, especially if the pump shuts off too quickly, that liquid refrigerant in the evaporator will want to naturally migrate to the condenser. And it wants to do that because the condenser suddenly became the coldest point in the system, and the liquid refrigerant is naturally attracted to that point. It wants to be at the coldest point. So you literally have that liquid refrigerant just draw itself right out of the evaporator and try to move into the condenser. In the process of that happening, especially if the pumps have shut down and we no longer have flow, you enter into a freezing saturation inside of the evaporator with liquid refrigerant still there that is trying to migrate, like actively migrate out of there. Because we still have standing liquid, and because we've now entered into a freezing temperature, a saturation temperature, and if we have pure water, or even if you've got some glycol, like, do your calculations to figure the differences, but we get into a freezing state regardless of what's inside of the evaporator tubes. That will cause a freeze on the tube bundle inside of the evaporator. And that's all it takes. From the research I've done on this, it is that really cold condenser coil that in a low ambient condition, when I say low, I mean it's pretty freaking cold outside, and it rapidly drops the condenser coils down below the evaporator temperature, and that causes that refrigerant to start to migrate, and just that whole process lowers the saturation temperature of the liquid refrigerant in the evaporator, which then allows us to actually start to freeze. So some ways to mitigate this is pump control. Other ways to mitigate this is isolation valves on the system, which takes us over here to the this is a YVAA specifically. So here's our compressor, and right here, this is showing the suction pressure, but in these machines there is a isolation valve right here. It is a refrigerant compatible butterfly valve that they've inserted in there with an actuator on top. It's got a big red, I think they're 120 volt actuators sitting right here on top. When the compressor shuts off, these actuators close. The reason for that is, these are using a falling film evaporator. So is a RTAC. We know that because our liquid comes in to the top of the evaporator. So just like it does, the line on a RTAC leaving the EXV assembly will feed into the top of the evaporator. So when we feed into the top of the evaporator, we know that we have a falling film style evaporator, even if sometimes the manufacturer's literature may call it a flooded. You'll see that sometimes, but if we're going to get real technical, we're talking about a falling film. Either way, this can still happen. And when I brought this up in a community post, I actually had some York fellas who had experience with these machines when they were just hitting the market, and they didn't quite have the actuator control logic set up just right at that time, and they were having issues with like this refrigerant migration freeze was actively an issue with these early YVAAs, which they corrected via I think software firmware updates, which they adjusted how they controlled the suction isolation valve. So in that case, to kind of recap, part of what would happen is, okay, so we shut down, we have a really cold ambient conditions. That would lead to the liquid refrigerant that's standing in here, which the bulk of the refrigerant on these machines is going to be in the evaporator, even with a falling film. Majority of the system refrigerant is going to be stacked here. So in that case, the condenser coils, fans shut off, everything shuts down for that particular circuit at minimum, but just in general, like just say the machine shut off entirely. The condenser coils can rapidly cool down in cold ambient conditions. Now, we're not talking seconds, but we are talking within just a few minutes time. We go from what coils were maintaining, say 100 degrees of average temperature, something along those lines, to all of a sudden we're down into, say, the 30s, 20s, something like that within a few minutes time. That's a very, very rapid change for a system like this. When that can happen, that liquid refrigerant wants to be here in the condenser. And so it starts to do everything it can, which if we don't have isolation on our suction side, it will, my understanding of this is it will actually come through the compressor side of the system, and that's how it will mostly migrate. Because with a lot of our machines, our EXVs, everything on the liquid side coming in through the metering device, on all of them that I can think of, when we have an EXV, they close fully. So this side is technically isolated, but this side is not. Even if there's a discharge check valve, the thing is, though, when we have this dramatic drop in temperature, which then ends up lowering our pressure because of pressure-temperature relationship, those discharge check valves end up getting neutralized because we end up equalizing, and then at that point, this refrigerant is going to have a path through the compressor. That's why it made such a big difference to have this suction isolation valve on the YVAA. So, yes, this refrigerant then starts drawing off, and it starts migrating its way into the condenser. More and more of it trying to stack in the condenser during this cold off cycle. And then as that process is happening, we are causing the standing liquid that is still in the evaporator to drop in saturation and eventually get below our freezing point and start to cause freeze on the tubes, particularly if we've already stopped flowing water at the wrong time. So you're at risk of this when we're in a condition where our outdoor ambient is very low, and there is a risk that, or that ambient is especially below whatever evaporator saturation or standing temperature we would have. Okay, so if we're going to have a condition where our condenser coils are getting colder than what our evaporator is going to be standing at, and we have a flooded or falling film evaporator, then we are at risk of these migration freezes. Okay, now the reason is, when we come over here to say this is an RTAA example, and it's just a very basic one but the reason I want this one is because this is a DX style evaporator. Now, mind you, in reality, they don't actually come in one end on the refrigerant circuit and out the other. Well, actually not, I'm sorry. I take that back. I think they actually did on some of the larger systems. Anyway, the point is, this is a DX style evaporator where the refrigerant is actually inside the tubes, water's on the outside. So these, and part of what we saw in the CGAM manual was it talks about the braze plate heat exchanger is not at risk for refrigerant migration freeze. It gives us more flexibility on how we control the pumps, and we don't have to worry about the evaporator as much in low ambient conditions because of migration. Now, we still have to worry about it in terms of just actually freezing due to low ambient conditions. That's still a problem. But we're not concerned about a migration freeze because of the style of the evaporator itself. And so with these, the refrigerant, it will still migrate. You will still have some of that stuff, but we don't have to worry about migration mitigation, right? Which would be a way to say that, because of where our refrigerant is inside the tubes, or in a brace plate, like it's in the brace plate itself, and we don't expect to have or those same migration issues and getting into a freezing temperature inside of the tubes does not have the same effect as a machine where the water is in the tubes and we freeze that water and it expands and ruptures the tube. Very different scenario than these DX styles where the water, if it was to even freeze at all, it would try to freeze on the exterior side of the tube, which I've not known any cases at all where that's a problem. That's just reading the manufacturer's literature. Like, it's just never been a concern that I've seen come up, particularly in this case with the refrigerant migration issue. Okay, so that's why with these machines where we've got a DX shell and tube evaporator, or we've got a brace plate heat exchanger, we don't have to be so worried about the migration, which is what majority of machines were for a very long time. They were this setup. Not all. Carrier and Trane are both ones that have used flooded or falling film evaporators in their air-cooled screws for quite some time. But York now has come out with, their YVAA, and we're seeing more of these screws because of the efficiency, right? All this comes back to efficiency. Why do we see more of these evaporators? They're more efficient than the other styles, but they bring unique risks with them as well in these environments. The big one being the migration mitigation. And so just to kind of recap on that, this is a condition where in cold ambience, the condenser coil becomes the coldest point in the system when the machine shuts off. And if we don't have a way to control migration from the evaporator, or at least continue flowing water during that time frame, we run the risk of that migrating refrigerant causing the evaporator saturation to get below our freezing point. When we get below that freezing point, especially once those pumps have shut off, we then risk a tube freezing and rupturing just because the machine turned off and it was really cold outside. So that's the core premise of what a refrigerant migration freeze is, and it comes back to the style of evaporator we have as to whether or not it's even a concern. And then if it is, like the RTAC, the solution there was the machine needed to control the pump, and it would run the pump for an extra period of time if it was in a migration condition, if I remember correctly from reading. And then the YVAA solution is we're actually just going to isolate to the suction line so that once we shut off, we have our EXVs isolate on the liquid side, so there's no migration there, and our suction line has a butterfly isolation valve that we can close and isolate that, so it completely traps that refrigerant in the evaporator and just doesn't allow a migration to happen, or at least not at a scale that's going to cause the low saturation temperatures in the evaporator. A very interesting read, by the way. Highly recommend, if you want to go just look up on it more yourself, go check it out. How you doing, Sterling? I see you there, Michael. Afternoons. Hold on. How are you, sir? I'm doing well. Holidays are well. A little heavier. Here you go. So does that mean you can recover the charge from a CGAM without water flow? I am not going to say the play it safe answer is no. It is still recommended to flow water with water flow on any heat exchanger. Now, Do I get super technical on that answer? And do I have some opinions? Yes. Am I going to make that a recommendation because crazy, like some wild hair, crazy stuff happens in our field? No, because for me, it comes back to the risk. Okay. If water flow is an option, even if technically we could probably get away with it, then we should flow water just because it's an option, and the risk of what it means if we are wrong or something like just the bizarre happens, which happens all the time. In that scenario, like it's just not worth it, right? It is not worth it at all. Even from a case of, okay, so we can't flow water, consider draining the evaporator. On a DX evaporator or a brace plate, do you have to go all out and like really drain the heck out of that thing like I would want to do with a flooded or falling film evaporator? Probably not. We probably don't have to go as hard to get all the water out as I would want to do with the others, but I would still want to do something, right? It's just like I said, it comes back to the risk. The risk is not worth the little bit of hassle you save yourself, which it may be more than a little sometimes. Um, yeah, I would still flow water, right? I would still flow water if it's an option. I don't quite get why the is not at risk though. Brace. I thought brace plate was very fragile. So one, if memory serves, I literally just finished, I guess, going through the manual, but I think um the CGAM actually pumps down. I could be mistaken on that. I think the CGAM actually pumps down. I guess we could pull that up. I could verify in the staging sequence if that is true. Because here, let's just take a quick look at it. We'll pull up the newest version of the manual. Cycle over here. Let's come back here where the staging sequences are. Now, in terms of other than if we weren't pumping the circuit down. Let's see, here we go. Wait to start. No. Shutting down. So pump. So close the EXV. Wait for EXV to close. 0 to 10 seconds. Yeah, de-energize all non-pump down compressors. And then, yeah, wait for saturated suction temperature to fall below. Confirm pump down termination. Yeah, so CGAM's pump down, right? So that's one of the things that's one reason why the CGAM, and let's see, I think most of the others that I can think of, I'm trying to think of just the various brace plate models out there. I think all of them go through a pump down procedure, which you wouldn't do with a flooded or falling film. You're not going to pump those evaporators down. That's actually where most of the refrigerant is stored during the off cycle. So that's not an option on those. Like that doesn't work that way. But most of the DX shell and tube heat exchangers were refrigerants in the tubes and brace plates that I can think of. They do go through a pump down cycle at shutdown. So they close the EXV and then they wait for the suction pressure to drop until they hit the target set point. So that's one reason why I think they're not at risk, right? Is because, well, there's no liquid refrigerant in there. Now, you do have to, and we do get back to a point of, okay, what if we have a shutdown happen that we didn't get to do a pump down, or it didn't pump down correctly? Like I said, sensors break, crazy stuff happens. Um, to my understanding, so let's come over here. One of the things about a brace plate, so let's say this is our heat exchanger. Got our pipes. And then here, we'll do this. We'll do blue and green, green being for water. Okay. So we've got our different plates, separation. Okay. Close enough. So when we're discussing, say this over here is filled with, say, liquid refrigerant up to this point. So all of this is liquid refrigerant. And then over here, we've got standing water all the way through, okay? So all this is standing water. I think one of the things that brace plates have going for them is, one, they're so much wider, and there's more room to expand compared to a tube. Okay, so a tube in this instance might be, say, 3/4 to 1 inch round. Actually, on these smaller machines like this that we would even be using this, they'd probably be even smaller than that. Maybe, I don't know, 5/8, 9/16, something like that. Anyway, we've got a small contained area, and so part of what happens in a tube scenario is we start to freeze here, and then we may kind of start to freeze here, and all of this is some form of slushy in the middle. But as the freeze gets worse, like all of this starts to freeze, but when it freezes, then it needs to be able to expand, except at some point it gets to a point where it can't expand any further, and this pocket of what gets trapped ends up kind of pushing out, and that's where our rupture happens. Where, I mean, we all know these brace plates, they can be what, a foot to 2-3 feet wide, on these smaller machines like this. And I think there's just more room for that expansion to kind of happen. And even if it did expand a little, I think it's just going to kind of cause those plates to flex some. Whereas with a tube, like, there's no give there in the same way that these brace plates have. Because, like, they're sealed on the edge itself, not necessarily internally, but on the edges of the tube. And I guess you've technically got the through ports where maybe it could cause a leak there or something. I don't know. I'm just kind of spitballing here, but that is, like, that's what I think of. Like, if I was to give a reason why it's less of a concern with the brace plate compared to others, being, given the arrangement, that would be my because it is still a confined space. Whereas, like, the argument with a DX shell and tube is, we've got, like, the water is on the open side of the shell. The water actually has quite a bit of room to expand, to be frank. And even with a brace plate, there's a whole lot more room for that expansion to happen than what we see inside of a tube. It's just not, it's a lot more restriction. It's a really good question, though. On that topic, Trane has implemented a pump down when shutting off during low ambient. I believe on the RTAF series. Okay. Trying to remember if the RTAF is flooded or not. I think the RTAF is, I think it's a, I guess I could pull it up here. I'm pretty sure I've got that manual. Pretty sure the RTAF is a DX Evap. Is it this one? No, that's the wrong one. I think I've got that manual. That's a TCAA. That's wrong. Water cooled. Give me just 1 second. Anyway, maybe you can see if your water is green, then we're talking about colors here, okay? Not green water. I'll deal with the manual thing later. Well, I can look up on that, Sterling, because I'm curious. I don't remember if those are DX or if they're um, falling film. From my memory, the ones I've worked on, I thought they were DX, which it would make the pump down cycle make sense. I guess, I yeah, it makes sense that they would pump down being a DX circuit. But like I said, I could be wrong. And maybe, if they are falling film, maybe that's their way of mitigating that migration freeze is because they're running really low liquid levels in that evaporator, and they are able to pump that out, right? Which would be an interesting way to go about it, because if they're holding any legitimate like standing liquid refrigerant in there, it would take quite a bit of running that compressor to get all that out of there. But I guess it may not be that big a deal. I may be overthinking it. They only leave gas in the evap. Yeah, exactly right. So that would be absolutely. Froggy, that was. Oh wait, no, hang on. A manual. That was the CGAM manual, CGAM manual from Trane that I was just reading on. So that's the one I'd recently been kind of going back through and refreshing. As they swimming on the. Might be right. Yeah. So yeah. By the way, um, this is something I'm gonna put out there. I thought it's been real interesting for me. So I really enjoy the reading, and I do want to stay on it and be more diligent with it. But sometimes I just get distracted or whatever. So one of the goals I've set for myself is I want to, like most nights, not every night, especially on what my Sabbath, which is Friday, Saturday, or Friday night into Saturday. But for most nights, I would love to actually post a snippet of whatever I'm studying at the time. That way, I can share it. You have it basically it holds me accountable to, okay, I'm going to study this machine. I'm going to go back through its book, and then I'm just going to share what I find interesting along the way, or if I have questions, or if I read something. Like last night, I was reading about Trane's lawn requirements, and I'm in the RTAC manual now, and I was just curious, right? So I just kind of chunked it out there as I just took a picture of what I highlighted for my own notes, and just get feedback. My point being, it's been a fun way to really expand and continue the thought process and really like make the reading more engaging, is actually like taking a picture of it and then sharing it and just maybe mentioning why I thought this was interesting, or if I have a deeper question that others can come in and engage with. And that's something that um, I've been curious, if that's something y'all might consider trying at some point. Pick a manual, and like I said, as a means of accountability for me, I want to post that and I want to share that, and that desire to do that and have that discussion holds me more accountable to actually doing it, because if I can't have the discussion, I can't make the post if I don't actually read and have something to post or to share. So I don't know. I know some guys are similar to me, and like creating those kind of consistent habits can be kind of difficult for yourself. I'm just wired different in that way, I guess. And so I think about it. Pick up a manual, read something. If you find something interesting, take a picture of it or a screenshot, whatever it is you want to do, and just post it. And think about, can I do this once a day? Right? Um, I don't know. It's just it's been a fun experiment for myself. Advice for a Trane OEM tech that has switched to Daikin OEM. Hmm. I don't know that I have any specific advice. I do find. Okay, how about this? I'll share some observations of what I see between like Daikin and Trane from a design perspective. Which kind of plays into like how you see or think about the equipment and what you're gonna do on a daily basis. So to clarify, I personally have not worked for an OEM. I've not gone that path. I have always been third party independent contractor on some level. So, and just to put that out there, so I don't know from personal experience what it's like transitioning from one OEM to another or otherwise. But from your particular case, going from Trane to Daikin, one of the things that I think Trane does really well is they really simplify the mechanical a lot. And that's a big focus that I see from Trane that is different. They, in my opinion, they probably sacrifice a lot of incremental efficiency gains for the sake of simplicity. That's my view on it. I don't have like inside information on that. It's just that's my view on the difference between what I see Trane do and others. So now Trane has gotten far more complicated with their controls and what they've done, and they have some fairly complicated machines, but when you compare what they are designing compared to others in the market, you can see the difference pretty clearly. Like Trane really prioritizes simple design, simple concepts. It it doesn't feel overthought, and that is something that I find with say York or Daikin or heck even Dunham Bush with some of their machines. They they get pretty complex pretty fast with them just trying to do all kinds of things that serve one main goal: improve efficiency, make the machine run better. I don't think one is truly better than the other. I really don't. Um, I think that it comes back to what does the application need and what are they looking for? And yeah, just what are the options on the table? What can the manufacturers provide to that? So I would say that's one of the big things that I would expect you to run into is you're going to see that Daikin just goes a lot further to optimize the machine than what I'm used to seeing Trane do. They just they will go to a whole other level with it. Um, what that means though is your complexity of what you're going to see, the possibilities of what could be wrong become more. Um, the in some cases maybe understanding the back end concepts deeper might be a bit more necessary, but I don't even know because even with Trane, like while Trane's designs are like honestly fairly simple when you look at them. There's not a whole lot of extra spoof going on like you'll see with some. Like some machines, they've got lines and tubes and wires and stuff ran absolutely freaking everywhere. Whereas Trane is like, it is very minimal. It's very, very minimal. But they're still using a lot of very advanced concepts. So like you still have to learn a lot of advanced stuff. They're just doing it in a very simplified way. Comparatively, okay? I say all this in comparison to. I think for Trane though, it gives them the ability to have a more streamlined factory line. It's a less complex machine, makes it easier to produce. The more complexity, the more components, like all of those things add to the quality control issues and speed and cost of producing that machine. You would think it would add to reliability, and in some cases it probably has. Like there probably is some extra reliability to some of their designs, not all of them, but some of them. And I'll give an example. Like the Trane CV series, like they honestly handle surge really well, really well. Out of all the chillers I've worked on and all the centrifugals over time, I've had the least issues. Now they still surge, don't get me wrong, they still have that issue, but I have the least amount of problems. And I can push those boundaries a lot harder with those Trane CV machines than I can typically do with other brands. And it just comes back to the basic design and the basic layout, like just their whole approach to Trane versus others. Most everybody else is using a high speed impeller, even if it is a multi stage compressor. They're running high speed machines. Trane's just a very simple single shaft low speed on their CVs. So, yeah, I think that's what I would that's my thoughts on it from a high level perspective. They're pushing a lot more boundaries. I would say Daikin is. They're pushing a lot more boundaries to try to achieve whatever operational metrics that they find important at the time. Other than that, in terms of people, like if I've gotten a ton of feedback, people really enjoy working for Daikin. I've got a lot of Daikin technicians inside of Chiller Academy that I work with routinely. Like they're people really enjoy, at least here in the United States. The feedback I have from techs in the United States is Daikin has been a really nice place to work. For guys who have been with Trane for a long time, their feedback tends to be they really like Trane. There's also young guys I work with from Trane that they really like it there, right? So I think it just kind of becomes a personal fit of which culture do you fit best in and their approach and how they go about it. I do know from a good personal friend, Jason Johnson, like they've done a lot. Daikin has because he works for them here locally in the Central Texas area. They've done a lot to really take his training seriously and really get him up to speed. And I think it's one of the benefits to working at an OEM is they take training to a whole nother level and a lot more seriously than what I see we tend to be able to do as a third party. And it just becomes these OEMs have the ability, like they've got equipment sales and all this stuff to like back up their bottom line, where when you work as an OEM or as a third party mechanical shop, I mean, sure, you have equipment sales and stuff, but like our profits are built around the jobs we do and constantly having technicians having downtime due to different trainings and like going through all this extensive stuff. It's just not as feasible as it is for the OEMs. And I think that's one big reason why OEMs tend to offer a lot more training to their technicians than non-OEMs tend to be able to get. Now, that's not true across the board, but that is a pretty consistent trend that I see. Okay. It's like workout motivation. Like The Rock used to post at the gym. Yeah, there you go. Okay. Yeah, talking about the reading the manual. I don't know. Jason may be a bit upset. Me and him were excited about the Bills game yesterday, and it didn't pan out so well. So he may be taking a quiet day. I don't know. Doing a crane lift. Just be careful out there. Keep your head up, eyes up. Pay attention. Those cranes. I've seen some. Which if you're used to doing it, you know. But just be careful. Trane started overthinking quite a bit with the newer units like the CMAF, 4 pipe, or even the RTSF. Are those their heat pump systems? Here, I guess I can look that up. I'm curious. I'll do it over here. CMAF. The CM Trane. CMAF. Okay, so we've got a manual here. See, air to water multipurpose scroll. Yeah, so this is a heat pump. Cooling capacity, heat pump mode. So, in fairness, Sterling, so the CMAF I would assume is their scroll heat pump, and then the what was it? The RTSF is I would assume is their screw uh heat pump. I guess I can look that up. I'm just spitballing here, but just kind of what I'm used to with Trane's identification. Yeah, okay, yeah. Yep. So it's a screw being the R. So R for Trane means rotary. So when you see the R, it's typically a screw machine, and yeah, these are their. This looks like a heat pump. Okay, I'm not gonna go crazy off into that, but in fairness, um, the okay, yeah, you said it's just a regular screw water cooled. But it's more of a modular case, right? So it's a modular build. So all right, that one's fair too. So what I see with the modular and heat pumps, because even the heat pumps that I see, a lot of them are built in kind of a modular design, or at least they feel like it when you look at them and when you're working on them. It's like it's really kind of feels like the whole multi-stack modular spiff or spoof or whatever. Anyway, I think in fairness, these are kind of painful systems to build, modular or um, heat pumps. And I think so. To your point, yeah, Trane probably is really going off the rails with some of the complexity, and so is everybody else, right? So that's not a justification for I'm curious to see long term, right? Because I would bet that because Trane is newer. I'm gonna say newer compared to others to the modular game, right? So it's probably a different team that's working on that engineering, and yeah, I would say it's probably just a different team, and that team is not the same as their other traditional core teams that are working on their legacy lines. I would assume this may not be true, but I would assume, and so because of that, it may take some time before that legacy kind of this is Trane's identity and how we design things fully filters into those designs as they begin to kind of flush out and Trane makes changes and improvements and just learns things from it. I don't know, it'll be something be interesting to watch long term. But yeah, a screw with a brace plate heat exchanger is interesting. You don't see hardly any of those. But it's not surprising though, right? Yeah, it's not surprising at all that from a modular standpoint, they're going to start going that path. And that's one of the tricky parts of the modulars. You have to try to account for so many factors machine could be installed in. I mean, it's just, but they're hot right now. Like, modular systems are absolutely freaking everywhere. So, I don't know. Why do low pressure machines surge? So, yeah. And it's not even a low pressure issue, but just why do machines surge? Let's talk about it. Okay. So let's first just kind of quickly discuss what a surge is. So a surge, when we use that term, we're actually describing a centrifugal style compressor. So they're not a positive displacement compression, which is what your scroll and screw and reciprocating compressors are. These are considered dynamic or aerodynamic compressors. They they work entirely differently in how we achieve a raise in pressure from a low pressure zone to a high pressure zone. With the regular, like, let's just go with a screw compressor, we're actually smashing the refrigerant into a smaller space until we eventually force it into a higher pressure because we compacted it. With a centrifugal, we're actually adding a lot of kinetic energy through velocity, and then we convert that into potential. Now, we don't have to go crazy off into this. I'm just kind of giving a high level, and it's okay if you don't fully understand everything. I will say that these are things that I go deep into inside of Chiller Academy in my certification course. I do see the question, do I have Europeans within the academy? Absolutely. The academy is global. I've got somebody from just about from majority of countries, I would say it that way. Um, Asia, Europe, the African continent, South America, Australia. Like, I've got guys from all across the globe at this point. We're pushing up on 4,000 students, almost at 4,000 students now. And so yeah, if you really want a true in-depth on this, I would say, like, you can really get into my certification program, spend time in there, and like, I can really break this down. And there are also, you have the ability to ask questions, and I can comment on it, give you feedback, stuff like that. So because a centrifugal does not directly compress, we don't have a set of valves where we're preventing that refrigerant from coming back like we do with screws and all these other designs. Like, they've got mechanisms, check valves, that are able to prevent that high pressure from coming back into the low side, and we just constantly push more and more and more. Centrifugals don't work that way. We can look at this example of an impeller here. Let's flip over here. So with this impeller, the refrigerant's coming in and we're coming out. Okay, so this would be your inlet eye. This is your discharge rim coming out into the diffuser. So out here we've got this diffusion ring that surrounds this and this refrigerant. So this would be spinning. Yeah, it should be looking at it from this angle, should be counterclockwise. So this is going to be spinning like this. And as it does, the refrigerant is then slung out all the way. And then we come through our volute and go out our discharge pipe into the condenser. Okay? So what ends up happening is something is causing, and it doesn't really matter what. Now, it matters if we're going to troubleshoot and fix it. But we're having a condition where we get a high lift. All right. High lift is, or lift in general, is the evap minus condenser pressure equals our lift. This is different from compression ratio. Okay, compression ratio, we're getting the absolutes and we're dividing them into each other to get a ratio. Centrifugals, we just use a different value known as lift. So it's just simple subtraction as to how we get that value. The point is, these impellers can only take so much of that difference. Once we get above a certain point, we have a surge happen, which is where this higher pressure gas on this side of the compressor backfeeds into the suction side. If you have a machine that is actually monitoring inlet suction temperature, you can see surge many times. It'll be a quick blip, but you'll see the suction temperature sensor right here at the inlet of the impeller will suddenly spike in temp and then drop back down rapidly, right? Those kind of changes are the surge happening. You're seeing hot discharge gas touch this side of the system, which is something we never want to see happen. And so something has caused a high lift condition. That high lift is overcoming what the impeller can do, and which is causing the refrigerant to backfeed through the impeller, which is very bad for the machine. Now, as to the low pressure side of this, low pressures have extra variables than normal machines. Let me say that a different way, than positive pressure or high pressure machines. So with a high pressure machine, our refrigerant system is in a positive pressure, and we are able to operate above atmospheric pressure. So what happens when we have a leak on a system with, say, 134A in it? Refrigerant leaves the machine and we lose refrigerant. With a low pressure machine, at least part of our, if not our entire system, is operating in a vacuum. We're below atmospheric pressure. So in that case, what happens when we have a leak? Atmosphere gets into the machine. What is atmosphere comprised of? We have water and nitrogen and some other stuff, but mostly water and nitrogen, right? That nitrogen is a non-condensable. So those non-condensables constantly getting drawn in a scenario where we have a leak will end up causing the same issues we see with any system, a split system RTU that had non-condensables in it, had some nitrogen or something, or vacuum wasn't pulled correctly, whatever the case. We have high head pressures. I guess that's what we see when we start dealing with non-condensables in the system. High head pressures means what? Higher lift. So because of the high lift due to non-condensables, now we start affecting our impeller's ability to move that refrigerant properly. So now that's just a reason that a low pressure would have an issue with surge more than just a high pressure machine. But we still get into a whole list of possible reasons. Okay, and a lot of it does come back to just what is causing the lift condition. So is it GPM through the heat exchangers? Either heat exchanger, okay? So if either heat exchangers does not have proper flow through it, or let's see, liters would be LPM, liters per minute, instead of, anyway, convert this to what I'm in America, so I use GPM. In a GPM scenario, like, we have to make sure we have enough GPM. Okay, we have to have enough flow. Maybe that's a better way to say that. Our flow through the heat exchanger. So HX, heat exchanger flow, is a very common reason that we would have surging issues, or if we have fouled tubes. Fouled. So when our tubes get fouled, that means that there's soot, mud, debris, silt, something is coating the tubes and is preventing heat exchange, okay? This can happen on the evaporator and the condenser. So don't just look at it as a condenser issue. This could be a evaporator problem as well. And maybe the evaporator has some trash in it, or it could be a water problem. I've had loops where it wasn't chemically treated. The loop is rusting out. It literally looked like liquid rust pouring out when you would open a valve. In that particular case, water didn't exchange heat so well. It had way too many contaminants in it, and we ran really high approach values. So something you're looking for with each of these is high approach. I'm covering a lot of stuff here that I don't know if you're familiar with or not. It's okay if you're not. All of these are basic fundamentals that we want to learn when we start getting into these chiller conversations. These approach values directly is impacting our lift value. Okay, so approach, if you don't know, is let's see, it's our saturation. So sat minus leaving water temperature of our heat exchanger. Okay, and now if this was on the condenser side, or no, if this was on the evaporator side, it would be inverse. So you shouldn't end up with a negative here. So if you end up with a negative, just flip the numbers. But ultimately, our saturation of the heat exchanger minus the heat exchanger's leaving water temperature. This is true for condenser and evaporator. And my focus is like freaking out here. Come on. This is true for either heat exchanger. So this approach, if we have a bad approach value for that heat exchanger, that also means we have a higher lift. Okay. So in an example of a condenser with dirty tubes, if we normally run an approach of 2 degrees, but now we're running an approach of 5 degrees saturation, or 5 degrees difference, I mean, between the saturation and the leaving water temperature, that 5 degrees means that our lift, our pressure difference, is now higher compared to the evaporator, because the evaporator wouldn't have changed, but our condenser is now running a higher pressure. Higher approach means higher lift. And so these are true high or low pressure machine. It's got less to do with being a high pressure or low pressure. It's more to do with what is causing the surge to begin with. Comes back to the lift. Then we start getting into all these other concepts. Yeah, so heat exchanger flow, fouled tubes, a refrigerant issue, whether that be some kind of contamination, whether that be a charge issue, whether that be control. If we've got metering valves not working correctly, not feeding enough through, we've got some kind of filter somewhere causing us a problem. Yeah, refrigerant issue, or we could add to this oil migration. Okay, so oil migration becomes a refrigerant issue where we've got oil stacking in the evaporator specifically, and that oil is causing a higher approach value. So it may not be fouled, may not be flow, it could be oil, and that oil ends up causing a high approach, and then that high approach leads to high lift, and which then leads to surge, right? So it's all kind of a stair-step effect. So this could happen on any machine that is a centrifugal, and then we have our non-condensables, which is where we get into the low pressure side of this. So this, when we start discussing why is a low pressure machine surging, these are the parameters we need to start digging into. Is why is this happening? Like why are we dealing with this as an issue as a whole? So yeah, if you have any more specific questions on that, feel free to throw them in there. I do see a thumbs up. So I'm happy to go deeper into something more specific. But hopefully that kind of gives you a good starting point at minimum. Hey, Jason, good to see you, bud. I was just telling everybody we had an interesting evening. So I did end up watching the game, by the way. I had to DVR it because I had stuff I had to do, but I did finish it last night, and holy crap, man! I was gonna text you later today and talk about it, but my main question here, Jason, is do you just at least have some nubs left for fingers? Now, even if you don't have nails or maybe the top end of them are gone, but do you at least have some nubs left, man? That's what I'm worried about. Fighting lift right now. Tower bypass isn't functioning. I have a heat recovery, chillers, comfort. Oh, so you're at that um, Templifier. You're at that Templifier plant, yeah? Hey, dude, they actually, I think they played fairly decently. I think they had a pretty decent game. I will say, I've been watching the Eagles the whole season just for fun. Um, and that was one of the best games that they've put together this season, like by far. So they brought it to the table with uh they brought it to the table, man, and I would challenge them to repeat that performance twice because I'll be honest, like that was a hell of a performance on their part compared to how they've also done for a lot of the season. So I'm just saying. Uh, hey Jason, by the way, we had a fella earlier in the stream. So Jason is a Daikin tech, so he converted from third party to Daikin. We had a fella though, he wanted to know about like transitioning from Trane to working for Daikin OEM and just kind of any advice at all on that, being that you're from Daikin. Um, yeah, being that you're with Daikin, like, just what are your thoughts on working with Daikin here? You can just throw it in the chat, and just do you have any suggestions, any thoughts, any opinions? Yeah, just feel free. It's up to you. Let's see, kind of catching up, especially the EMEA models become energy efficiency requirements of the EU market. They have to bend over back. Yeah, yeah. Well, that's the thing, when when the efficiency requirements are easier to achieve, you have a lot more flexibility and not having to just go ridiculous with your design to squeeze every ounce of watt out of the machine. And so, like it does make it easier to simplify the overall design and process and da 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 da. Um, Whereas, when you start having to hit those metrics, those simple designs, they just may not cut it, right? Yeah. Anyway, do you service tech gen chillers? No, no, not really. If I'm happy to talk about it, I don't mind. I can look it up. Tech gen. I'm kind of curious. I'm gonna add this to my list of things to research. Come over here. But by the way, how does the stream seem on y'all's end? Is it super choppy, like the video specifically? Is it having like a weird choppiness like it did last time? If it is, please let me know. I'm still trying to tune my laptop settings in my new laptop. Side note for the RTAF, I found it page 66 of the IOM. It talks about operational pump down during low ambient. Startup shutdown, safety satisfied, figure sub mode operational. Okay. Huh. Yeah, I've got that manual somewhere. See, part of what I do is as I get manuals, most manuals are not labeled per what the manual is, so I always end up having to relabel them. But sometimes I find them as I go, or I get them from somebody and I save them. But I I don't get to relabel them immediately. So then, like right now, so anyway, I've got it in my Trane folder. I just got to go find which one it is, and I'll have to look that up because I'm very curious on that Sterling, on the what style of heat exchanger they're using on those. Yeah, you answered the bat signal. Don't fight the lift. Just take the stairs. Yeah. No. Yeah, you're right though. Don't fight the lift. Fix it. Right. Don't fight it. Fix it. Yeah. See why do we have a lift issue? Love working for Daikin. Well ran and organized. Every district is different. Our branch is awesome and everything seems to work well. Yeah, so one curiosity from a Daikin standpoint, like do y'all have like a South North American region kind of thing? And then that is that how it's split up, or because I know at least one, if not a couple of the manufacturers have that type of setup where the US itself is or split into like, yeah, the US I think is like two parts. Some of them are like four parts. They've got different segments depending on how small they wanted to make their management structures. Thank you, Sterling. Okay, just making sure. I I think these last adjustments are gonna do pretty good. Oh, so y'all do North America and Canada out of the same. Interesting. Okay. Where my comfort cooling chillers aren't running high lift, but the Templifiers have enough heat from the comfort cooling condensers to make heat. Yeah. Okay, I wouldn't have expected that, Jason, honestly. I would have thought Daikin would have segmented their leadership uh, to smaller sectors than that, but there you go. Now we know. So you're trying to, yeah, that's an interesting conundrum because even with that case, artificially raising the condenser water set points doesn't really do you much good. I wonder if do you have a bypass control on that plant? Like, is there a bypass on the condenser water that maybe you could restrict more on the cooling tower side and try to let the templifiers take all that, or you may have already done that. You may be in 100% bypass right now. Granted, I don't even know if that system can even handle that, uh, or if that would be too much. That's some serious. So how about this? Everybody may not be familiar with what we're discussing here. Uh, oh, the bypass isn't working. Well, what about manual? Well, I guess you want to be cautious with manual. So if I assume is your bypass like locked in 100% open just for safety? Yeah, I see where you're in a real conundrum there because if that bypass isn't working, you're not able to restrict your towers, and we're in what the 40s today, um, here in Texas. Yeah, the Templifiers Evap. Right, exactly. Well, that's why my thinking would be we could. I say we you if the basically the Templifiers, if they're capable of even being um if they're even capable of handling the loop volume to just act as the cooling towers at that point. I don't even know if they'll handle that much GPM through them to satisfy the whole loop. But like I said, though, if that bypass isn't working, like that puts you in a really difficult spot because yeah. So if folks don't know, and Jason is here, he can correct me, but I'm gonna take a swing at. So when we talk about templifiers, what we're discussing is a larger scale version of what we would use for, say, or how about this? Is a different way to do heat recovery. All right. So everybody's probably at least heard about heat recovery with a VRF system, but heat recovery with chillers can also still happen. It has been around far longer than VRF heat recovery has, to be frank. So there's a couple of ways that heat recovery can be done. One of the common ways is there will be a heat recovery heat exchanger connected to the chiller, right? And I guess I could pull one of those up. Give me 1 second. Let's go to centrifugals, schematics. We've got a picture here with a Trane diagram. Right there. Okay. So, dadgummit. Do it every time. Every freaking time. Screwed the pooch there, boys. There we go. Try that again. Over here trying to get fancy with it. Now I'm just screwing stuff up. Okay. So this is an example of what heat recovery can look like. So in this particular evaporator, compressor, condenser heat recovery, right? So in this case, we've got discharge gas is getting pushed out into the should be still condenser, but then that superheated discharge gas can get up into this heat recovery cylinder. And as it gets in there, we'll have a separate heating loop flow through this in order to capture the heat from the condenser before it even gets to, or before it has to process through the condenser tubes. And so essentially we're just robbing some of the heat. This does take load off of the cooling tower, and then we can repurpose that heat. So it's the exact same concept as VRF, if you're familiar with that, where we're literally taking heat from the evaporator, putting it into a hot water loop, not a condenser water, a hot water loop, and then sending that hot water to do other work somewhere else, right? Whether that's comfort heating, whether that's say just manufacturing process, whatever the case may be, we're just repurposing that heat. So this is a more common example of a heat recovery system. And you'll also see this like the scroll CGAMs. If you read into the manual, they have partial heat recovery condensers. And I can show you that quickly here. So if we pull up a CGAM manual, we can see right here. So this is an example of the CGAM's heat recovery. So this is where the condenser, the discharge gas from the compressors go through these and then go through to the condenser to then finish the cooling process to get them back to a liquid and flow to the metering device. So again, this is just how like an air-cooled scroll Trane chiller would manage it through these heat exchangers. Now, what Jason has, let's see. So we've got, well, I'll try to just use a simple single chiller. So we have our primary chiller. Okay. For this chiller, we've got our evap and condenser. Okay. On the chill water side, we've got standard chill water flow. Okay, chill water coming in, chill water leaving. Everything's normal there. On the condenser water side, we'll start off with this red here. Actually, no, we'll use purple. Purple. These would be going to our cooling tower, okay, or CT. Now, this is a fundamentally normal chiller here. Nothing really fancy or crazy going on. But we have an extra chiller down here. So this would be our evap. And this would be this is going to be a CH. This would be the condenser. So in this case, we have taps coming off and coming through this chiller. And then we have through the evaporator of this chiller. And then we have our condenser water lines. The condenser water lines are tied to a heating loop. This loop can be tied to a number of things, but I think like in Jason's case, I think these are tied to a set of boilers. So if this chiller can't maintain enough heat output, I believe there's a set of boilers for backup heat. Jason can correct me on that. Either way, this is providing heat throughout the building, and so we're literally taking what is our comfort cooling chiller. We're sending what would be condenser tower water out to the condenser tower. Gee whiz, cooling tower water. What would be cooling tower water? We're sending that out to the cooling tower to be processed like normal. But then we have a Templifier. Okay, and I think Templifier is technically a Daikin term, if I'm not mistaken. But we have the Templifiers that are then bringing that heat into its evaporator so the condenser water from the comfort cooling chiller into the evaporator of the Templifier, and then the Templifier is then putting that heat back into the system. So it's another way of recapturing what was originally comfort cooling heat and then reusing it somewhere else for another purpose. Again, it doesn't matter if this is comfort heat, doesn't matter if it is like a process system. Maybe they've got a manufacturing line where they need some hot water for it to do whatever job, right? None of that is really that relevant. But so when the system we're discussing here with him is that. Now he also says that, just to kind of give you some extra context, the bypass on the condenser water side, which would normally be here for like controlling cooling tower temperature or condenser water temperature control. And there's going to be times where we don't need to go through the tower due to lower loads and low ambient conditions. We want to maintain a little bit of heat here because, well, we can't go too low on our lift either, right? So that's a whole nother conversation. But the point is, these will have a bypass on them, and his bypass is not working. So because his bypass isn't working, it really restricts him because he's got a low load here. But because this has a low load, that means this is also getting a low load because they're directly inverse to each other. But then we can't artificially increase load here very easily because the actuator on this valve is not working. Now, you could say, well, why not just manually control that valve? Well, that's a very tricky thing because the consequences of this valve closes and you either go too far, like you can't sit and manually control this by hand enough to balance this system and keep everything in alignment. Like, that's just not reasonable, and it's not something where you can just kind of set it part way and walk away from it and expect it to be good. You can't do that here, or at least I wouldn't recommend that. That's a really quick way to cause the whole system just to completely crash altogether, where right now it's at least functioning. So yeah, so he's put in a really tight spot because this valve can't control. Because it can't control, we are processing through the tower on some level. I don't know if he has open loop or closed loop. I would assume they're probably open loop towers, which is even worse to his benefit. It would be better if they were closed loop, in my opinion. But at least for this particular situation, maybe not from an efficiency perspective, but from this situation, either way, so the towers are constantly removing heat just from the sake of the water's got to go through them in the first place. We can't stop flowing through the towers because our bypass isn't working. So that means that now the Templifier chiller has to also share with the cooling tower in terms of rejecting that heat, or they're kind of fighting and working against each other. But we can't artificially, like, just because we raise the set points here doesn't automatically mean just more here on the Templifier side. Like, he's in a really weird spot. Let's see. Yeah, the Templifiers aren't big enough. 200 tons and the comfort cooling, yeah. So they're just not even able to move. So we wouldn't be able to go full bypass anyway, which technically we wouldn't have to, as long as the bypass was working. Yeah, it's a heating chiller. So they're designed to be a heating source, not cooling. Right. And so they're designed, so to add to that, like with a comfort cooling or a regular process cooling, we normally, the chiller's designed to target a our evaporator water at, say, what, um in the 40s on average, right? And if we get into certain processes, maybe it's down into the 30s, 20s, whatever. But we're trying to target specific um, lower temperatures. And with this Templifier, I would expect that evaporator to be designed for warmer waters, right? So we're talking, what, maybe on the low end 60s, probably up into the 80s and 90s entering water on the evaporator side. So that would be one, um that'd be one at, like, that's one of the differences that we're going to see from a design perspective, is what is the evaporator trying to process through it from a temperature standpoint. Now, the other side of this is where this Templifier is going to get very similar to a heat pump. See, with heat pumps, they're not only designed for a specific cooling evaporator temperature, but they're also designed for high condenser water temperatures, and specifically condenser water leaving. Like, that is really where the heat pump side of this. So for this particular chiller, I think he said 125 was his design leaving water temperature. Set point's 135. Okay, so that kind of gives you, like, this chiller is doing its best to load itself up enough to achieve 135 degrees of leaving condenser water. So what would be condenser? So whereas we're used to seeing, we're going to load based off of evaporator leaving water, this machine is loading and controlling its capacity based off of condenser leaving water, if I'm saying this correctly, Jason. So it it wants to see the set point achieved on the condenser side, not the evaporator, which is part of what he's saying with it being a heating machine is reverse. So with this one, we're focused on what is our leaving water temperature on the evaporator. This one, we care about what is our condenser leaving water temperature. Um, yeah, so your Templifiers, he's saying that, like, these are typically designed for like a 60 to 80 degree evaporator side water in order to achieve that 135 on the condenser side. And he doesn't have any backup right now because the boilers that are supposed to be the redundancy heat are not working. Oil fed, centrifugals, and my minimum. So you've got some McQuays in there. Minimum condenser water for these chillers is 65. Yeah, yeah, because again, just some more context for everybody. If we get too low on the condenser water side, like below that 65, we start affecting oil return. So will start having a lot more issues with oil stacking in the evaporator, and it won't make its way back to the oil sump, and we can't control oil return properly when we start dipping too low on that. So that's just something that we got to just be aware of. We got to think about. You can also get into like choke territory. So different machines have different, it's like, so you have a surge and choke line. I'm not going to go crazy off into choke right now, but like if we get too low of a lift, we could get into a choke situation, which has a similar effect to a surge, is the way I would say it. The bypass is an 8-inch line. Yeah, and the main tower feeds are, yeah, okay. Well, and here, Tom, choking the water down, like, well, choking the water for flow, what that really does, So you're saying maybe choke it at the comfort cooling condenser? But the thing is, if we choke flow there, we're going to increase lift further. And I think part of what Jason's trying to work through is like I think he's maybe already running at some of those limits. Yeah. Yeah, they're running hard because they're trying to just suck so much heat out of it. Which, I mean, again, that gets back to your tricky point is you're pushing that compressor hard on the Templifiers to achieve the leaving water set point of 135. But then that means you've got really cold water coming back to the chiller condensers, water that's already been processed through a cooling tower, right? So not only do you have that cooling tower chilling it down just from the low ambient right now you've got this Templifier. His point of running that low 65 degree, like that floor on what he's allowed to do, he's up against it. This is fun, Jason, by the way. Thank you for jumping in, bud. Seen a plant where the RTH are in charge of the heating for a part of the city. The chilled water side is either used for process applications or they use geothermal. Yeah, yeah, hard to balance is I'd say an understatement. Doing an 80 ton, I do see that YK question. I'll circle back to that in just a moment. Doing an 80 ton CGAM rebuild, your recommendation that a system like this would require a 4-hour decay test? Yeah, so yes, I recommend doing a system like that with a CGAM 80 ton circuit or 80 ton chiller, so it'd be a 40 ton circuit. If you could do at least 2 hours, give it at least 2 hours. But if you have the time, a 4-hour decay would be like super solid. It's a smaller machine, it's a small circuit. So that also means the charge is lower. I'm going to be less hardcore about those values for that small of a machine. And I get real particular with the larger machines because our risk is much higher, right? So if you can get a 4-hour on that decay, be awesome. And you can walk away absolutely no concerns. But if you can at least get a 2-hour and you're looking really stable at 2 hours, and like if you just really got to call it, then so be it. I mean, you can. It's you did your due diligence at that point because there's a lot of folks that honestly they give it half an hour, if half an hour to an hour, like if they even give it that long, as long as they don't see that micron gauge haul butt in the wrong way, they call it, right? So just in terms of you doing your due diligence and what I would want to do in that situation, that's my opinion there. Yeah. Yeah, so you've got a low load, Jason, on those chillers. I don't envy you. I don't envy you at all, Bubba. You not only did you eat that crap sandwich last night, you eating it again today. I'm sorry, bud. Hopefully your week gets better. That or you could honestly, with the way you are, you're probably having a blast right now. To be frank, like you're probably this is right up your alley. Sure, it's a headache, it's a pain, it'll drive you nuts, but my gut is you're a kid in a candy store right now. All right, I don't know. York YK chiller discharge superheat is 36 ish at 40% load, and drops to 25. Is this normal? Also, lift pressure range for, yeah, this is a, so one follow-up question I have, and is on this YK, what, it sounds like you've probably got a constant speed, or your if it's not constant speed, then your drive is running at a 60 hertz and is locked in there potentially. So if you can confirm that, that would really kind of navigate my response a lot more. Can I read that? Okay. On a York YK chiller, discharge superheat is around 36 degrees at 40% load and drops to 25 degrees at 70% load. Is this normal? Also, what is the normal lift pressure range for YK chillers? And you do confirm that it is a constant speed. The answer is yes, it is absolutely normal and expected. So to, how do I want to explain this? Discharge superheat for a constant speed centrifugal is different than what you would expect to see with variable speed or even with other compressors. A big reason for that is the cooling of the compressor itself. So what you're seeing is as the machine increases load, more refrigerant is being put through the impeller. That higher volume of refrigerant is allowing the compressor to be cooled more. Because a constant speed machine, because it's not changing RPM, we're running at a consistent, like this is our speed, which for your YK should be like 20, at full speed, 24,000 RPM, something like that. So at full speed, you have a set amount of heat being generated by friction of just rotating at that speed. You have your gear assembly in there. You have all kinds of things creating heat. So the less refrigerant we move through it, the less heat is being given to the compressor, and that is reflected in the discharge superheat. So you'll see that at low loads, you'll have high discharge superheat with a constant speed centrifugal. And then at high load, where that machine is, that those guide vanes are really opened up and you're really moving a lot of refrigerant through the impeller, you'll see the discharge superheat drop. And the more load you can put on it, the lower you'll typically see that discharge superheat get. This is absolutely normal and what we want to see. Now, variable speed machines are different because we can actually control the RPM. So as the machine unloads, we are lowering the total RPM, which means lowering the total friction being generated and the heat the compressor is producing. As that heat is reduced, you'll see that discharge superheat fluctuate more with the load on the load on the compressor. Okay, so you won't have the same like super high discharge superheats at low loads like you would with a constant speed machine, because we're actually allowing that compressor to slow down, and it is reducing the amount of heat the compressor is making. This is also why the guide vanes, whenever you look at them, they have this little pinhole, and I can show this here. So with our guide vanes, there will be this little divot hole left right in the middle, and I'll illustrate it here as best I can. Let's do this. So right here, all the vanes will kind of meet up and marry, but they'll leave this little hole here. And you'll see this is across the board. This is not unique to the York YK or anything. that hole is for cooling. So they've ran calculations and they know that for this machine to run with the vanes fully closed at all, we need to have at minimum this circumference of an opening in the guide vanes in order to give us just enough cooling. Now, these compressors should not run closed like that for an extended period of time because of cooling. These are suction cooled compressors. But they can run for a short period of time with them fully closed. Then that's what'll happen at startup. That can happen at shutdown. Like there's different times, or if we're going into in and out of surging, you'll see these close off like that. So those are some conditions where we need to have that opening for motor cooling, but that's why that opening is there. One of the few machines that this is different for are the ones that use liquid injection on the volute or inside of the yeah, it's directly into the volute. So there are like Daikin or McQuay is one of these that they have liquid injection into the volute of the compressor in order to allow it to be quieter. A machine like that, you'll see discharge superheats like -1 or -2 degrees at times, and those are really low because of the liquid injection into the discharge of the compressor itself. But that's not the actual impeller like superheat, if you will, coming out. Then that liquid is there for noise dampening purposes to make the compressor quieter, have a lower total audible reading to it. So in terms of the normal lift, so the trouble is lift that the compressor can manage. Well, let's see. That's a constant speed, so I think it's normally at around, was it 60 to, no, you're dealing with a 134A machine. Specifically those York YKs. By the time I'm hitting about 60 pounds of lift across the okay, it's just not this simple. All right. That's a hard value to give because it's dependent on load. So at high loads, when we're talking, 8 to 10 degree split across the evaporator, temperature difference across the evaporator, you could run some really crazy lifts. We're talking 80 to 90 pounds of lift from condenser to evaporator, and it'll cruise right in that zone all day. And like at those high loads, I mean, yeah, by the time you start getting up into the, say, pushing high 90s to 100 pounds of lift, you could start running into surge issues. But you then turn around, yeah, and I'm referencing this from a 134A perspective. That's what a YKs currently use. You then turn around and make this a low load scenario or a partial load where we're not having to derate the machine heavily, and then we still try to run those higher lift values. We end up pushing into either a surge or a choke. Like we have to be real careful of that. So my point being, the lift you can maintain at lower loads is lower than at higher loads. So as the machine unloads, the lift you can do also decreases before you start going into surge. So that's why it's really important, like if you can give condenser relief or lower those condenser water temperatures as the load reduces, that is best for the machine, because then because your condenser water temperature drops, your lift is also reducing because the head pressure drops with the water temperature getting lower, and that lower lift with lower load is what we need. So that's just something to be aware of. Now I've started really preferring to think about lift in terms of saturation temperature. So
what I mean by saturated lift is, um, if we take the, a condenser saturation of 80 degrees and an evaporator saturation of 40, well, that's a 40-degree saturated lift. Okay. And I find that if we start looking at it in those terms, things start to really apply across different machines, and the model matters less. And it still matters, but it matters less. Okay. Because one of the things is, um, like if you learn pressure lift on a YK and then try to go to a different machine, um, the lift may the lift may be different, or specifically like you go from that high pressure to a low pressure, you're talking very different pressure differences, but in actuality the saturated lift is fairly similar. So you can have a very similar saturated lift where you're going to have issues and be okay, whereas the pressure like the actual lift via pressure is radically different, right? So anyway, from a saturated lift perspective, um, once I start hitting about what 40 to, it's really more like 50 degrees of saturated lift, somewhere in there, depending on my load, that's when I know I'm start getting concerned. So, um, yeah, between 40 and 50, especially for a partial load application. So if I'm dealing with partial load where I don't have a full 8 to 10 degrees across my evaporator, then I really want that lift, that saturated lift, to be down in more like the 20s or 30s. I don't want to see it up in that 40 plus range. Now, if I've got a fully loaded machine and I'm running that 10 degrees or so across my evap, then yeah, there's a lot of machines you can push to 50, 60 degrees of saturated lift, and they'll run like that all day. They won't even blink at it. But again, there's enough load to support the machine doing that, and we're not trying to derate that machine. So my goal is I'd rather you learn a more holistic view to understanding the discharge, superheat, and lift values than trying to learn that specific machine. Because I did this for a long time, and it makes it difficult when you go from one model to another. It feels like you have to relearn all these values. When in reality, if you learn kind of the whole, call it the holistic baseline of just how these things work, you realize that you could just learn this one fundamental thing, like saturated lift values as an example, and then you realize, okay, so this can be applied across the board, and then my refrigerant, the pressures I'm running at, all those things matter a lot less compared to what is my saturated temperatures. Um, yeah, so I'm not going to give you hard set lift values for a YK because it is so variable. And what adds to the complex, if you had a variable speed YK, that would add to the complexity, because as we reduce RPM, we reduce um, the amount of lift we can maintain, and I could spiral off into a whole separate conversation there just on that. But with a constant speed, it's fairly simple. You've just got an inlet guide vane to manage. Maybe I doubt you have a VGD. I don't think you'll have a VGD without a VSD. So you've probably just got a PRV, the pre-rotation vane, inlet guide vane, same thing. Um, yeah, that's my answer. Let's see. Constant. They still have comfort cooling. Yes. What is it? Yeah, it's a hospital. There you go. Okay. So dehumidifiers year round, and even still, like just in our environment, Sterling, you got to think our winters. So right now we're in some of the coldest we'll see most of the year. Here in another month, we might see in the 20s, right, for a few days. but we're at about the coldest we're going to see for the bulk of the year with a day like today, where we spend majority of our winter in maybe the 30s and 40s at the worst. And that's for about a 2 to 3 month period. That's about it. So needless to say, in large commercial buildings, hospitals, facilities like that, yeah, we comfort cool year round in a lot of these cases, whether for dehumidification or even just regular comfort. Our systems may never shut down. So that is something unique to where we are compared to where I know a lot of you other guys. Like once y'all hit winter, it's full shutdown of the whole plant, and it won't even turn back on for several months. We don't have that. Oddly enough, I really enjoy the calls like this. Keeps me on my toes. Yeah, yeah, they can be fun. Go full speed on tower. Pump. Less efficient. Yeah, I don't know, Tom, if forcing the tower speed on the pump would really have the effect you're looking for. I think it just comes down to the actual cooling load. Like it is just lower, and it's low enough that without the redundant heat, like it's just you're in a lose-lose scenario there. Like you just the solution is we need more heat than we have, or we need the boilers to work. we we need the boilers to work, and they don't. So, well, speaking of boilers, I've got a good friend that Eric Johnson that I've been thinking about bringing on, or I need to figure out how I'm going to do it. That's the main issue. I haven't, but I was looking at doing a boiler special where he could come on, and we have the same format we're doing here, but just he and I, and we have a day where we just talk about boilers, and y'all could get to know Eric. I know that he started a podcast. It's was it Boiler Wild, I think is the name of it. Anyway, Eric's a really cool guy. I'd highly rate. He's based out of Florida, but he comes from the Midwest, up in the northern state. I forget exactly which one offhand, but he's got a very deep boiler background. Really cool guy. So curious to hear your comments. I've had several people ask for a boiler Q&A session. I am not a boiler guy. I can I work on them to a degree? Yes. Am I going to sit here and try to explain a slick of it to you? No, I'm not. I'm not trained enough to even attempt it, much less I'm just not doing that. So anyway, thoughts on doing a boiler special where we have somebody come in and do a um, yeah, do a boiler Q&A here on the channel. I've noticed that most controllers that I've come across don't even have a lift value. What's up with that? Is that because we can't even agree whether it's based on pressure? So manufacturers really hone in on the pressure side of it. From my experience, I don't know that I have seen a manufacturer reference it as saturated lift. Um, what and how I came about that was just in conversations with different folks. And I had a guy on LinkedIn one day that we got to discussing it. He brought it up, and I just started asking questions. And like he explained to me just his training, and he was taught, and he looks at it that way. And like I spent a lot of time kind of thinking about that, and it really just struck me like this is actually a really good way to think about this. I like this. So I've completely made that switch to saturated lift. And um, I guess there are some panels that will mention what the lift value is, but the thing is, what makes it challenging with chillers is there's a lot of stuff that are, call it expected, okay? The you are genuinely just expected to understand what lift is, how to calculate it, and how to use it. It's not spelled out for you and it's not given to you. And we see this in a lot of scenarios where the data is there, the saturations, the temperatures, like the data is there. They just didn't create a graphical thing where they calculated it for you. The expectation is you do that math yourself. I don't need to do it for you via software. And I think that really just summarizes. Like there's just the expectation of you can do this calculation yourself. We don't need to run the math for you. We don't need to do that. We're not going to put money and time into this thing in the software just to make it easier for the technician, when it's just that's it. That's what I see as an expectation just within the industry. It would be awesome if they would just give all. It would also be awesome if they give us like all of our superheat calculators. There's a lot of machines out there. They don't give you the superheat number. Many do. Don't get me wrong. Many do, but many don't. And you're just given here's your suction temp, here's your saturation. Figure it out. Or I've had it to where they'll give you the suction temp and they'll give you the pressure, but they don't even give you the saturation temperature. You have to convert the saturation yourself and then do the superheat calculation. Like I've worked on those machines. So I don't think it's an issue with agreeing on what number to use. I think they just haven't built it in out of choice. Just personal thoughts. In basin heat we trust, that's right. I don't know anything about boilers. Over here, it's the heating engineer's job. I guess they like to compartmentalize job descriptions. Well, you also get into what we would consider very kind of unionized environment with where you're at. And for anybody that doesn't know, that means Europe. So, like in the EU, I would say the closest thing we have to that in the States is what we see on the union side, and things are very compartmentalized. You have this description, you have this job, and that is the only thing you even think about, much less do. At least that's my perception, right? I've not worked in that environment. I've worked with a lot of companies who are union. Don't get me wrong. I've become very familiar with the unions just on this whole journey of running Chiller Academy and the HVAC Time brand, right? So I've had to get familiar from that standpoint, but I would just say, yeah, that is what I see with those types of organizations. And from my understanding, talking to you and many others across the pond there, y'all just have a very union structure compared to what we have. So anyway, yeah, like I said, I've still got to work out the details on how to make the stream work. I got to figure that out. Well, once I do and I get scheduled with him, I really am trying to get that done here while we're still in the winter. I wanted to do it over December, but my December has just turned into pure chaos for me. So that has not happened. I'll work on it. Okay. Really appreciate everybody. I'd love to see you in the academy. A lot of what we've talked about today, it is in the certification course at chilleracademy.com. I'd love to see you there. I also have my in-person hands-on training coming up in Houston in March and April. There are limited seats to those trainings, and they are a 4-day class. You can send me an email. I will send you more details from there. If you're wanting to really start this journey, really get into it, and you haven't gotten engaged at chilleracademy.com yet, like I really, really encourage you to get into that side of it, or get into the academy, fill it out, see what you think. I'm there to support you. That's where I spend a lot of my time. And MTT, make the time for your family, for your spouse, for your kids. They need you. I'll see you guys later.